In this paper, we propose an image-based cross-view geolocalization method to estimate a UAV's global pose. We use the current UAV image and nearby satellite images as inputs to two neural networks, a scene localization network and a camera localization network. This is in contrast to previous cross-view methods that focus only on scene localization. Our global camera pose output is a weighted sum of the network outputs. We also propose a framework to integrate our cross-view geolocalization output with visual odometry. For our dataset, we simulate UAV images in Google Earth and obtain satellite images from Google Maps. We create around 33,000 image pairs from 12 different cities across the US. To test our integration with visual odometry, we simulate a flight approximately 2.5 kilometers long in Google Earth. For our scene localization network, we implement a Siamese architecture composed of AlexNet layers. We calculate the distance between the output feature vectors from each branch and train the network on a contrastive loss function. The network learns to generate closer feature vectors for matching image pairs and distant feature vectors for non-matching pairs. For our camera localization network, we implement a Siamese architecture with AlexNet convolutional layers. We use a hybrid classification plus regression architecture to get the camera pose estimate from the network. The horizontal position is classified into cells, whereas the vertical position and orientation are regressed. Our network performs better compared to previous regression-only architecture. Also, our network generalizes well to unseen image pairs in the test dataset. We implement a Kalman filter to integrate visual odometry with our cross-view geolocalization output. For visual odometry, we use incremental pose estimates from OrbSlam2 in the prediction step of the filter. Global pose corrections from our cross-view geolocalization are used in the correction step. We test the performance of integrating visual odometry with our cross-view geolocalization architecture on the simulated flight data. The blue line shows the trajectory of integrating OrbSlam2 with our scene localization network plus our hybrid camera localization network. Our method obtains a position root mean squared error 50% lower than other methods.